Asking a question like, is the brain a digital computer, seems silly at first sight, but the more we learn about how our minds function, the more we realize how computer-like we could be. One fundamental problem, as mathematicians now realize, is that they made a crucial error 50 years ago in thinking the brain was analogous to a large digital computer. But now it is painfully obvious that it isn't. The brain has no Pentium chip, no operating system, no application software, no CPU, no programming, and no subroutines that typify a modern digital computer. In fact, the architecture of digital computers is quite different from that of the brain, which is a learning machine of some sort. A collection of neurons that constantly rewires itself every time it learns a task. A PC, however, does not learn at all. Your computer is just as dumb today as it was yesterday. So there are at least two approaches to modeling the brain. The first, the traditional top-down approach, is to treat robots like digital computers and program all the rules of intelligence from the very beginning. A digital computer, in turn, can be broken down into something called a Turing machine, a hypothetical device introduced by the great British mathematician Alan Turing. A Turing machine consists of three basic components: an input, a central processor that digests this data, and an output. All digital computers are based on this simple model. The goal of this approach is to have a CD-ROM that has all the rules of intelligence codified on it. By inserting this disk, the computer suddenly springs to life and becomes intelligent. So this mythical CD-ROM contains all of the software necessary to create intelligent machines. However, our brain has no programming or software at all. Our brain is more like a neural network, a complex jumble of neurons that constantly rewires itself. Neural networks follow Hebb's rule. Every time a correct decision is made, those neural pathways are reinforced. It does this by simply changing the strength of certain electrical connections between neurons every time it successfully performs a task. Hebb's rule can be expressed by the old question: how does a musician get to Carnegie Hall? The answer: ceaseless practice. For a neural network, practice makes perfect. Hebb's rule also explains why bad habits are so difficult to break, since the neural pathway for a bad habit is so well worn. Neural networks are based on the bottom-up approach. Instead of being spoon-fed all of the rules of intelligence, neural networks learn them the way a baby learns, by bumping into things and learning by experience. Instead of being programmed, neural networks learn the old-fashioned way through the school of hard knocks. Neural networks have a completely different architecture from that of digital computers. If you remove a single transistor in the digital computer's central processor, the computer will fail. However, if you remove large parts of the human brain, it can still function, with other parts taking over for the missing pieces. Also, it is possible to localize precisely where the digital computer thinks, its central processor. However, scans of the human brain clearly show that thinking is spread out over large parts of the brain. Different sectors light up in precise sequence, as if thoughts were being bounced around like a ping pong ball. Digital computers can now calculate at nearly the speed of light. The human brain, by contrast, is incredibly slow. Nerve impulses travel at a relatively excruciating slow pace of about 200 miles per hour. But the brain more than makes up for this because it is massively parallel. That is, it has 100 billion neurons operating at the same time, each one performing a tiny bit of computing, with each neuron connected to 10,000 other neurons. In a race, a super fast single processor is left in the dust by a super slow parallel processor. If one cat can eat one mouse in 1 minute, how long does it take for a million cats to eat a million mice? The answer is obviously 1 minute. In addition, the brain is not digital. Transistors are gates that can either be opened or closed, represented by a 1 or a 0. Neurons too are digital. They can fire or not fire, but they can also be analog, transmitting continuous signals as well as discrete ones. Next time, we're going to take a look at the concept of a screen room, or four-wall screens, how it could impact the way we communicate with our friends and family, and how we organize ourselves, how close we are to actually achieving such an idea. So tune in next time and we'll find out together.